Hey, welcome back to Following Science, the podcast where I explore the most fascinating topics in the world of science. I'm your host, Virtual Parl, and today I'm going to be embarking on a journey through one of the most profound and enigmatic concepts in physics: time. Time governs every aspect of our existence, from the rhythm of our daily lives to the vast evolution of the universe. Yet, despite its omnipresence, the true nature of time remains one of the greatest mysteries in science. So, sit back, relax, and join me as we unravel the complexities of time. Let's start with the basics. What is time? At its core, time is a measure of the sequence of events, a way to quantify the intervals between occurrences. It's an abstract concept, yet it's fundamental to our understanding of the universe. Time is something that we constantly measure, track, and try to manage. Now, we often take for granted that time flows in a linear fashion, moving steadily from the past through the present and into the future. But is this really the case? According to Albert Einstein's theory of relativity, time is not an isolated entity, but it's intrinsically linked with space, forming a four-dimensional continuum known as spacetime. This theory revolutionized our understanding of the universe. Now, in classical physics, space and time were considered separate entities, with time being absolute and universal. However, Einstein showed that time is relative and can vary depending on the observer's motion and the presence of gravitational fields. Einstein's famous equation E equals mc squared indicates that energy and mass are interchangeable. Similarly, his theory of general relativity suggests that massive objects cause a distortion in space-time, which we perceive as gravity. This distortion affects the passage of time, causing it to slow down near massive objects, a phenomenon known as gravitational time dilation. Now, one of the most fascinating predictions of relativity is time dilation. This effect, predicted by Einstein's theory, states that time passes at different rates for observers in different reference frames. Now, there are two primary scenarios where time dilation occurs. First, due to relative velocity, and second, due to gravitational fields. Now, when an object moves at a significant fraction of the speed of light, time appears to slow down for its relative to a stationary observer. This has been experimentally confirmed using precise atomic clocks flown on high-speed jets. Now, upon returning, these clocks showed a slight difference compared to those on the ground, confirming the time dilation effect. Now, imagine you're an astronaut traveling on a spaceship at near light speed. To you, time on the spaceship would feel normal. However, to an observer on Earth, your clock would appear to tick more slowly. This means that if you embarked on a long journey and then returned to Earth, you would have aged less than your friends who stayed behind. This phenomenon, known as the twin paradox, highlights the non-intuitive nature of time in relativity. Now, according to general relativity, time passes more slowly in stronger gravitational fields. This means that the closer you are to a massive object, such as a planet or a star, the slower time moves relative to somebody far away. This effect is crucial for the accurate functioning of GPS satellites, which must account for the differences in the passage of time at different altitudes to provide precise location data. For instance, clocks on GPS satellites are further from the Earth's gravitational field, and that's why they tick slightly faster than those on the ground. Now, of course, this is why engineers must account for this difference to ensure the accuracy of the positioning data provided by these satellites. Now, while relativity provides a framework for understanding how time can vary, it doesn't explain why time seems to have a preferred direction. This phenomenon, known as the arrow of time, is deeply connected to the second law of thermodynamics. This law states that entropy or disorder in an isolated system always increases over time. Now, this increase in entropy gives time its irreversible quality, distinguishing the past from the future. Now, think about it. You can easily mix milk into coffee, increasing the overall entropy in the system, but you can't unmix it. This asymmetry in time's behavior is evident in countless processes, from the aging of living organisms to the cooling of a hot cup of tea. Entropy also explains why we remember the past but not the future. Our memories are records of low entropy states, and as time progresses, the entropy of the universe increases, making these low entropy states less likely to occur in the future. Now, moving from the macroscopic world to the microscopic realm, we enter the domain of quantum mechanics, where the concept of time becomes even more intriguing. Unlike in classical physics, where time is a smooth and continuous flow, quantum physics and quantum mechanics introduces the idea of quantized time intervals. leading to a probabilistic nature of events. Now, in the quantum world, particles can exist in multiple states simultaneously, a phenomenon known as superposition. When we measure these particles, the superposition collapses into a definite state, but the timing of this collapse is governed by probabilities rather than certainties. This probabilistic nature of quantum mechanics challenges our classical notions of time. Now, the uncertainty principle formulated by Werner Heisenberg further complicates our understanding of time. It states that certain pairs of physical properties, such as position and momentum, cannot be precisely known at the same time. This principle extends to time and energy, suggesting that there is a fundamental limit to how precisely we can measure the duration of events and the energy involved. For example, if we try to measure the energy of a particle very precisely, there will be a corresponding uncertainty in the measurement of the time duration of the particle state. This inherent uncertainty blurs the classical distinction between past, present, and future at the quantum level. Now, our exploration of time wouldn't be complete without discussing its origins. According to the prevailing cosmological model, the universe began with the Big Bang approximately 13.8 billion years ago. This event marks not only the origin of the universe, but also the beginning of time as we know it. Before the Big Bang, our conventional understanding of time breaks down, and we enter the realm of speculation and theoretical physics. The concept of cosmic time emerges here, providing a measure of time that is universal across the cosmos. As the universe expands, cosmic time allows us to track the evolution of galaxies, stars, and other celestial objects. This expansion of the universe also affects our perception of time. Now, in an expanding universe, distant galaxies appear to be moving away from us, causing the light from these galaxies to be redshifted, an effect directly tied to the passage of cosmic time. Now, black holes, the enigmatic remnants of massive stars, also play a crucial role in our understanding of time. These objects have intense gravitational fields that not even light can escape through them. According to general relativity, time behaves very differently near a black hole. As you approach the event horizon, the boundary beyond which nothing can escape, time appears to slow down dramatically relative to an outside observer. This effect, known as gravitational time dilation, means that if an object is falling into a black hole, would appear to freeze in time as seen from a distance. However, from the perspective of the object itself, it would cross the event horizon without any noticeable changes in the passage of time. Now, near a black hole, the warping of space-time becomes so extreme that our conventional understanding of time breaks down. Inside the event horizon, the roles of space and time can even switch, with time becoming a spatial dimension and space becoming a temporal dimension. This mind-bending concept challenges our everyday experience and highlights the profound impact of gravity on the nature of time. Now, beyond the scientific explanations, time raises profound philosophical questions. Does time exist independently of human consciousness, or is it a construct that we use to make sense of our experiences? Philosophers have debated these questions for centuries on end. One philosophical perspective is presentism, which holds that only the present moment is real, and both the past and future are mere concepts. In contrast, eternalism suggests that past, present, and future events are equally real, existing in a four-dimensional block universe. This view aligns more closely with the theory of relativity, which treats time as another dimension alongside space. Now, another intriguing idea is the concept of time as an emergent phenomenon. Some physicists and philosophers propose that time may not be a fundamental aspect of the universe, but rather an emergent property arising from more basic physical processes. This view suggests that our perception of time could be a byproduct of the way we interact with the universe at a macroscopic level. The study of time is, of course, far from complete. Physicists and philosophers continue to explore its mysteries, from the nature of time in the quantum realm to the possibility of time travel. Of course, while time travel remains a staple of science fiction, some theoretical models suggest that it might be possible under specific conditions, such as through wormholes or using exotic matter with negative energy density. Wormholes are hypothetical tunnels connecting different points in spacetime, which could, in theory, allow for travel between distant regions of space and time. However, the practical challenges of creating and stabilizing a wormhole are immense, and such a feat remains purely speculative at this point. Now, as I wrap up this episode, I just want to review through everything we've done. So first, we journeyed through the multifaceted nature of time, from its definition and measurement to its role in modern physics and the profound philosophical questions it raises. Now, time, while an everyday experience, remains one of the most profound and intriguing concepts in our quest to understand the universe. Now, I want to thank you all for joining me in this exploration of the physics of time. If you enjoyed this episode, please subscribe and share it with the fellow science enthusiasts. Stay tuned for more episodes where we delve into the wonders of science and unravel the mysteries of our universe. If you have any questions or topics you'd like me to explore, feel free to reach out and say it in the comments. Until next time, keep questioning, keep exploring, and keep following science. This is your host, Rutu Parl, signing off.